For decades, the story of space travel was all about fire and fury, right? The brute force of chemical rockets. But a new chapter is being written. And it's not with a roar, but with a silent, almost mesmerizing blue glow. This is what's powering our internet, our return to the moon, and really, the future of exploration.
I mean, just look at that thing. It looks less like an engine and more like a captured nebula or something. There's no violent explosion, there's no deafening roar. It's just a silent, steady, electric blue light that's pushing us into the future. This is a Hall effect thruster, and it has quietly become one of the most important technologies in modern spaceflight.
So, let's pull back the curtain on this incredible piece of engineering. What exactly is it? Where in the world did it come from? And why is this strange blue light suddenly everywhere we look in space?
That is the big question we're going to tackle. And while it totally looks like something straight out of science fiction, the principle behind it is this clever dance of electricity and magnetism that is fundamentally changing how we get around in the solar system.
And listen, this is not some far-off experimental tech we're talking about. I mean, right now, as we speak, Hall thrusters are the workhorses of space. They are positioning thousands of Starlink satellites. They're keeping China's Tiangong space station perfectly in orbit. They're powering NASA's whole return to the moon. They're even pushing probes like Psyche all the way out to asteroids beyond Mars. So yeah, this isn't the future of spaceflight, it's the engine of right now.
All right, so how do you get thrust from basically nothing but electricity and a little bit of gas? Well, it all comes down to taming one of the fundamental states of matter, plasma. Let's break this down. Okay, this schematic right here, this is the key to understanding the whole thing. It might look a little complicated at first glance, but the basic idea is actually surprisingly simple. At its core, this whole engine is designed to create a really elegant trap for electrons, and that's what makes everything else work.
So, at its heart, a Hall effect thruster is a type of ion engine. But what makes it special, unlike other designs, is how it uses this clever combination of a magnetic field and an electric field. The magnetic field creates a kind of barrier for electrons, and the electric field, well, that does the heavy lifting of actually creating the thrust.
It all happens in 4 key steps. So first, a neutral gas, like xenon, gets puffed into the chamber. Second, a magnetic field traps a bunch of electrons, creating this swirling, high-energy cloud. Third, and this is where the magic happens, these trapped electrons slam into the neutral gas atoms, stripping away their electrons and turning them into positively charged ions. And finally, an electric field grabs those new positive ions and just flings them out the back at incredible speeds. We're talking up to 80 kilometers per second. That stream of ions, that's the thrust.
Now, you might be thinking this is a pretty recent invention, right? But the story of the Hall thruster has this amazing, unexpected twist, and it's rooted deep in the Cold War.
So, while the basic concept was being explored in both the US and the Soviet Union back in the 60s, it was actually the Soviets who perfected it. The very first Hall thruster flew on a Soviet satellite way back in 1971. For decades, it was basically their secret weapon for moving satellites around. It wasn't until 1992, after the fall of the Soviet Union, that American specialists finally got to visit Russian labs and the technology was finally introduced to the West. And that eventually led to its first use on a lunar mission in 2003.
And you can literally see that evolution right here. On the left, you've got some of those early, really robust Soviet-era designs, and on the right, a sleek, modern Hall thruster module. The physics behind them is the same, but you can tell the engineering has just taken a massive leap forward.
Okay, so if these engines are so great, why don't we use them to launch rockets from Earth? Well, the answer comes down to one of the most fundamental trade-offs in all of rocketry: power versus efficiency. It's really the story of the tortoise and the hare.
Chemical rockets, they are the hare. They give you an immense, powerful kick of thrust, but they gulp down their fuel in just a matter of minutes. Hall thrusters, they're the tortoise. They produce this tiny amount of thrust, a gentle push really, but they are incredibly efficient, just sipping their fuel over months or even years of continuous operation.
And just how tiny is that push? Well, a typical 1.35 kilowatt Hall thruster produces about 83 millinewtons of thrust. I know, that number probably means absolutely nothing to you. So let's put it in perspective.
The force this engine produces is about the same as the weight of a single coin. Just resting in your hand, you would barely even feel it. Here on Earth, that force is, well, it's nothing. But in the frictionless vacuum of space, that gentle, constant push changes absolutely everything. And that is the absolute key right there. It's not about the strength of the push, it is all about the duration.
A gentle, relentless push, applied continuously for months on end, can accelerate a spacecraft to speeds that would require an enormous, totally impractical chemical rocket to achieve. It is the ultimate lesson in patience paying off. This incredible efficiency also comes down to what fuel you choose. Xenon has traditionally been the best performer, but it is incredibly expensive. So for a massive constellation like Starlink, SpaceX had to make a business decision. They started with the cheaper krypton, and now for their newest satellites, they've switched to argon, which is nearly 2,000 times cheaper than xenon. That's what makes operating thousands of satellites financially possible.
So, from a Cold War secret to the absolute backbone of the commercial space industry, the Hall thruster is now ready to take us even further.
This is the Lunar Gateway. It's a critical piece of NASA's Artemis program. Think of it as a space station that's going to orbit the moon, a staging point for missions down to the lunar surface. And guess what technology will keep it in its precise, very complex orbit? You got it, a powerful set of Hall thrusters.
So when you look at the landscape of space today, that blue glow is it's everywhere. It's the engine behind the Starlink megaconstellation. It's the station-keeping system on China's Tiangong space station. And it's the long-haul engine for deep space explorers like the Psyche spacecraft.
Really, the big takeaway is this. This technology has finally come of age. It's reliable, it's efficient, and it has unlocked a completely new level of capability for everything we do in orbit and beyond. It is the quiet, glowing workhorse of our time.
Which, of course, leaves us with a really tantalizing final thought. With engines that can sip fuel and push gently but relentlessly for years on end, the old limits of the solar system are really starting to fade away. So the only question now is, where are we going to choose to go next?